like we might have a 10 attendance today. I'm not sure, but let's see. Um, but a couple of administrative things before we jump in. We do have homework 7 due tomorrow, not today. In case you notice, the deadlines would be Saturday 5 p.m. and then part 2 deadline would still be the same on Monday 5 p.m. Any particular questions on homework 7, working with MATLAB? How's that? How's that coming? There's a few questions from some of you on the discussion forum. So if you're having trouble, make sure you look at those. I think there's some good hints there. And of course, you're free to post additional questions there. Mubin.
So when we're doing the indeterminate code, we have to input which element is redundant. We just put in the number, not in a, what do you call it?
Row?
In a row,
Uh-huh.
right? And then that's it, nothing else.
Yeah, so
depending on how we label each
if
element.
you looked at the few examples of the indeterminate trusses that are also available in the codes, yeah, there's two ways you can treat redundancies. One is a redundant element, and the other was a redundant support, right? So the same problem can be solved in many different ways by choosing different redundant elements, or actually not choosing any redundant element, but instead a redundant support. You have to make sure on paper that the redundant element that you're choosing makes sense. It should not be that you choose a certain redundant element that still leaves the remaining truss indeterminate. Does that make sense? You can choose a wrong redundant element even while you're working on paper using the force method. It's not that you remove any element and it suddenly becomes determinate. Usually you have to pick the right element to remove and make sure that the underlying truss after removal of that redundant element or that redundant support, the underlying truss is determinate. That makes sense? Go ahead, Praveen.
For the questions in the homework, we only have to take out one element.
Yes. For the questions in the homework, I think for both those indeterminate trusses had a degree of redundancy of 1. So if you pick the right element or if you pick the right support, you can reduce it down to a determinate structure. Any other questions? Okay, so let's jump back into the stiffness method, which is again a very computationally heavy method, which is why we don't want to do all of this by hand. So you'll get additional set of MATLAB codes that I wrote. And just a word of caution here, even though on the first slide, when we started talking about the stiffness method, I referred to chapters 14, 15, and 16 of your textbook. I feel that the way that the textbook ends up explaining the stiffness method is not the most easiest to grasp. So my approach will differ from their approach. They have so many transformation matrices for everything, which is completely unnecessary. If you follow my notes and my video lectures, I think it will be much more easy for you to understand how, first of all, the method works, and then also be able to use the MATLAB course that I'll be providing to you. So quickly, what we've done till now is basically what we want to do with the stiffness method is to be able to express local force displacement relationships for individual elements. And then somehow combine those force displacement relationships for all the elements in the structure, and using equilibrium, find out the unknown displacements. So keep in mind, this is a displacement method, meaning that the displacements, the unknowns are displacements. Okay, unknowns, if you remember from the flexibility method, the unknowns were redundant forces. Now we are using, our primary unknowns are displacements. So the idea is that if we can express forces in terms of displacements, then add up all the forces from all the elements, then we can solve for those unknown displacements. And what we've done till now is to express um, two things. One is a local force displacement relationship for truss elements. So we were able to say that in the local coordinate system, x prime, y prime, for a given element, you can find what those force vectors would be at those two ends, I and j, by simply using the fact that force in a truss element is AE over L times change in length, and that gave us this 4x4 system of equations that relates force and displacement in local coordinate system. And that last lecture, what we did was we took each and every subcomponent of that force. So there are two forces here, force at node I and force at node J. Similarly, we have two displacements here, displacement at node I and displacement at node J. All of these four vectors are in local coordinate system. And like I said last time, that if all your vectors are in local coordinate system, then you can't really add forces and displacements from one element that is oriented in one direction to another element that is oriented in a different direction. What we need to do before adding them is to convert all of these forces and displacements in a common global coordinate system. And the way we did that last time, if you remember, was using this transformation matrix that we had derived, cosine minus sine, sine and cosine. Given any vector, this transformation matrix will take you from a local coordinate system to a global coordinate system. And using this approach, we were able to express the same force displacement relationship for a truss element using a transformed stiffness matrix. So this relationship out here, this is Q times K, Q is equal to K times delta. This relationship is expressed in the global coordinate system. It is exactly the same relationship that we had for the local coordinate system, but expressed in a different coordinate system. And then finally, where we were last time, we were just about getting ready to use the fact that sum of forces on all the nodes of a truss has to equal to 0. And you remember last time we said that if we have these 7 elements, then each element is going to apply forces to its corresponding 2 nodes. And for example, for element A, this guy, it applies forces to nodes 1 and 2. So it contributes forces to these 2 rows of equilibrium equations. So what I'm writing here is the global set of equilibrium equations for this entire structure. Okay. And so similarly, we added forces for all these B, C, D, E, F, G members and just adding it to the correct location. Anybody remember why we had this minus sign? It says up there for the node. Why minus sign for the node? Go ahead, Mats.
It's like the opposites. At the node, it's in compression.
Right. So indeed, if you look at this diagram, the force at the ends of the element is what we calculated. That force is the way that I've drawn it looks like it is going to cause tension in the member. But we are not summing forces for members. We are summing forces over the joints I, J, and all the 5 joints or however many joints there are in the truss. The forces on the joints are actually pointing exactly opposite to the element forces. That's why we added this negative sign out here. So that's one thing to keep in mind. And where did these come from? These are all the external forces to the truss. Now, clearly, some of them here, for example, 10 and 0, that's the external force on node 2, 10 because it's 10, 0 because in the x direction there is 10, 0 in the y direction. Similarly, there is 0 in the 3y direction here. There is 0 and minus 10 on node 4. That also makes sense. It's nothing in the x direction, minus 10 in the y. and all the question marks denote the unknown reactions. Okay, so in this case, I have 5 unknown reactions, so I have 5 question marks, and even those reactions are external forces on the truss. As far as the structure, as far as the truss is concerned, whether it's an external load or a reaction coming from some support, it's an external force on the truss, right? So what we want to do is to just sum up all of the forces that are external to each and every element, and make sure that the sum of forces on all of these 5 nodes goes to 0. That's all that we did uh, in this expression. And maybe I'll also explain what's going on a little bit more in detail here. Um, so let me copy that and go to a separate new page. What we uh, this entire equation that we had up there is really a sum of 2 vectors. Okay, one is a vector that looks like QA1 plus QB1. In the second row, we have QA, QC, QD, QE. There's 4 elements connecting to node 2, so indeed we'll have QA2 plus QC2 plus QD2 plus QE2. And similarly, if you look at 3 QB3 plus QC3 plus QF3, and finally for Q4, QD4 plus QF4 plus QG4, and for 5 we have QE5 and QG5. So what we have here is a 10 cross 1. This is a 10 cross 1 vector. Why is it 10 cross 1? It looks like it's 5 cross 1. Because each one is a force on a node which has both x and y directions. So each one of those is a 2 cross 1. And if I have 5 of those, it becomes a 10 cross 1. This is the set of forces that all of the members in the truss apply on all of the nodes of the truss. And if we add to that, the external forces, then each of those 10 rows must go to 0. That's just a statement that sum of forces in the x direction is equal to 0 and sum of the forces in the y direction is 0 times 5 nodes. That's what this is, right? So this is something that we've been doing forever, but we are just writing all of those equilibrium equations in a very systematic way that can be automated. Keep in mind, these are things that we do not want to do by hand. We want to be able to automate the process for generating these. So essentially, it's a 10 cross 1 vector and another 10 cross 1 vector, and we want to make it go to 0. What are the unknowns here? The unknowns are displacements, right? And because each one of these forces for element 1, these Q1, QA1, QA2, these forces are the forces at the ends of member A. They depend upon the displacements at the ends of member A. So displacements really are the unknowns. What we'll do is we'll use these 10 equations to find those unknown displacements, because there are 10 displacements, right? 5 nodes, 5 times 2, there are 10 displacements. Before we do that, we have to actually express these 10 equations in the form where we actually have displacements explicitly in the equation. So now this is the most important step with the stiffness method. You have to still, what we did here was we assembled the element forces in this force vector. What we're going to do now is to convert each one of those element force vectors to something that looks like a big matrix, which we'll fill in, and actually that I'll ask you to do as an in-class exercise after I show you a couple of examples, and then multiplied with the unknown displacements. So displacements at 1, 2, 3, all the 5 nodes, both in the x and the y direction at each one of those nodes, those are the unknowns that we are trying to solve for. The right-hand side, some of the forces are known, some of them are unknown. So the unknown forces are what we are trying to solve for. It will so happen that you'll see that if the reaction at 1x and 1y is unknown, the displacement at 1x and 1y will be known. Does that make sense? If you look at this guy, reactions 1x, 1y are the unknowns, but displacement is known to me. It's 0 out there, right? So at a given node, only one of the things would be unknown. Either the displacement would be unknown, or the force would be unknown, or the reaction force would be unknown. Look at node 3. This is a special type of a node. In the x direction, the displacement is fixed, 0, and the reaction is unknown. But in the y direction, the displacement is unknown, but the force in the y direction is known. The force is 0, right? So this will always be the case that at a given node, either displacement or the reaction force would be the unknown. And given 10 equations, I can either solve for the displacement unknowns or the reaction unknowns. And I'll show you how to do that. But before we do that, as I mentioned, we are going to try to fill out this matrix because we want to convert these element forces into something that involves element displacements. So let's see how we do that. Anybody recognize this equation? Where is this coming from? What is this equation? Qi, Qj is equal to Kii, Kij, and so on, and delta Ij. What is this equation? These are indeed the member force, Q force, and delta displacement relationships. In what coordinate system? In the global coordinate system. We need that relationship to be in the global coordinate system. This relationship holds for each and every element A through G. I have a 4 cross 1 here. This is indeed 4 cross 1 because 2 times 2 cross 1, right? And each one of those members is contributing a 4 cross 1 vector to the force vector. So what I'm going to do here is I'm going to show you a couple of examples, and then I'll ask you to fill the rest of it out as an in-class exercise. I'll give you an example for element A. Clearly for element A, I have QA1 and QA2. That's equal to KA11, KA12, KA21, KA22. And again, all of these 4 things are, each one of them is a 2 cross 2 submatrix. And what is that submatrix? Let me show you that in a very quickly here. Up here. So this relationship of QA1, QA2, and a 4 cross 4, which can be then subdivided into a 2 cross 2. Right, so this is what is K11, K12, K21, and K22. But this is the relationship in the local coordinate system. We want to do a same thing in the global coordinate system. So if you remember, last time we derived the global stiffness matrix, and we said that this stiffness matrix would be essentially this 4 cross 4 transformation matrix multiplying this 4 cross 4 element stiffness matrix times another 4 cross 4 transformation matrix transpose. So the product of all of this, or the product of these three matrix multiplications would be a 4 cross 4 global stiffness matrix, right? And again, if I maybe just to show you what that might end up looking like, and I know this is all a little bit abstract in terms of all variables, but I'll show you a couple of examples with actual truss members oriented in different directions, and that will hopefully even make it clearer. But for now, let me just set up what I want to show you in a little bit. So we have these 4 cross 4 global element stiffness matrices in the global coordinates, right? And this thing here, there are these 4 2 cross 2 matrices within that. I cannot tell you what they are because these will be obtained by doing this complicated matrix multiplication, right? So 4 cross 4 times another 4 cross 4 times another 4 cross 4, not something you want to do by hand anyway. But what I'm calling KM11 is this 2 cross 2. This is KM2, 1 cross 2 or 1 2. And bottom left is KM2, 1, and the bottom right is KM22. So a particular element stiffness matrix for any truss element will always be a 4 cross 4. The numbers within those matrices will depend upon the orientation of that element, because depending upon the orientation of the truss element, the forces in the global XY coordinates will be different. So that's why I can't really tell you explicitly what they are. But you don't have to worry about that because MATLAB is going to solve for it anyway. So back to this guy. I want to express the forces from element A in terms of the displacements of element A. So clearly, I will have a displacement element A. Actually, the displacement doesn't belong to a particular element. It's a global displacement at node 1, global displacement at node 2. So I hope you agree that for element A, it is connected to nodes 1 and 2. So this is the relationship that holds for element A. And if I try to express or try to just substitute this relationship into this vector, into the global vector, the way to do that would be to write here KA11. The contribution at node 2 would be KA12. Contribution at node 21 would be KA21 and KA22. So all I've done is I've added the contribution from element A to this big system of equations. Let's verify. KA11 times delta 1 is equal to the right hand side. KA11 times delta 1 plus KA12 times delta 2. Everything else here right now is 0. So if you look at this, all I did here was this 4 cross 4 matrix times this 2 cross 1 vector. If I take this matrix times this vector, I would get the original QA1 and QA2, right? Which is what I need here. Okay. Now to add to it the contribution of B, 1 and 3, what we need to do, we need to express the same sort of relationship for element B. B is connected to 1 and 3. So what we need to do is to add KB11 at the 1, 1 location, KB13 at the 1, 3 location, KB31 and KB33, right? Can anybody tell me why did I add these two? Because they overlap. I mean, yeah, the location of those two overlap, but why add? Why not subtract or multiply or something else? Well, because if you look at the original system, we are adding forces from element A node 1. We are adding that to element forces from element B node 1, right? So if I want to get QA1 plus QB1, I need to add the components of KA11 times delta 1 and KB11 times delta 1. And this is a process uh, that if you write out, it will be much more clear. I'll do one more and then I'll ask you to do the other four members uh, by yourself and on a separate piece of paper by hand. And then I'll give you 5 minutes to do that. All right, so the next element is you pick which element should I add, because clearly since it's all addition, the order in which I add them does not matter, right? So I could add C, that's the next logical choice, or if you're curious to see, I'll add E, that is connected to nodes 2 and 5. So, um, and I'll remove this bracket because that's just a bracket that I wanted there to show you how it's working. But all right, so K plus KE22, and in 5 I'll have KE25. In 5 comma 2 we'll have KE52 and KE55. Okay, so you should already be starting to see some pattern that for each element we are adding these four quantities, four 2 cross 2 matrices in the correct location in the global system. And if we end up adding all of the components of all of these elements, we will get a system of equations that represents equilibrium um, for this entire truss. So go ahead, take 5 minutes, uh, maybe a couple of minutes, try by yourself, and then you can obviously consult with your neighbor. And on a separate paper, please, yeah, and that I'll ask you to turn in, and then we'll do it together. Uh, you mean for this guy? Oh, this. Oh, you want both of them? You don't have the handout with you? Okay. All right, so that's about as close as I can get to having both of them. And again, if you're not sure how to do it, let me know immediately. This is again not a test. Right, feel free to discuss with your neighbor student and see if you came up with the same answers. And if things are still not clear, please do ask us. Right. More questions? All right, let's bring it back. I'm sure you all have questions. So go ahead, ask. Don't make me read your mind. All right, so let's try to do this together and see if what we do here up on the board makes sense. First of all, is this process or what we are actually trying to do is that the objective of that should be clear. The objective is that we want to solve these 10 equations, and hopefully you all see that there are 10 equations in here. Just like I showed you a bit earlier, these 10 equations really are sum of forces x of y at each one of those 5 nodes. That's all that we are trying to do. And in order to be able to solve those 10 equations for the 10 unknown displacements, well, not all of the 10 displacements are unknown. Some of the displacements are unknown and some of the forces are unknown. So there are total of 10 unknowns between the displacements and the forces, and I have 10 equations, so I should be able to solve for all of my unknowns. And in order to do that, what we are trying to do is to express these forces in terms of their corresponding displacements. So if we can do that, then we have a system of equations which we know how to solve. So for example, for the way that we constructed this, the way that we constructed this partial matrix was by assembling the contribution of element A into this global stiffness matrix. We did that Ka11, Ka12, Ka21, and Ka22, and so on. So let me just go ahead and add the contributions of all of these elements. So element C, which is connected to nodes 2 and 3, and that's clearly up here. Nodes 2 to 3 is what element C is connected to. I'll add the contribution of that, which would look exactly, which would look very similar to this guy, right? Instead of A, it would be C. Instead of 1 and 2, it would be 2 and 3. That's all that the change would be there. So if I start adding that contribution, there would be KC22, KC23, KC32 plus KC33. Just that simple. Similarly for D, D is connected to 2 and 4. So I will have yet another contribution here, KD22, KD24, KD42, and KD44. We already added the contribution of E, so I won't add it again. I have F, which is 3, 4, connected to 3 and 4. So we'll add that, plus KF33, KF34, KF43, and KF44. And finally, we have G, which is connected to 4 and 5. So I'll have KG44, KG45, KG54, and plus KG55. And hopefully you're already seeing that pattern that I mentioned. How would you automate it? How would you automate generation of this system of equations? Loop over the elements, exactly like we did in the MATLAB code that you're working on right now. Right? All we did was we looped over all of these elements. Each one of these elements contributes 2 entries to the force vector and contributes 4 entries to the stiffness matrix. So at the end of this process, you will have the correct stiffness matrix, a vector of unknown displacements, and a vector of forces. What I'll do now is actually show you some numbers. And we are not going to crunch numbers by hand. We'll let MATLAB crunch the numbers, but we need to make sure that we are correlating each one of these steps that we've learned in the stiffness method, and we'll let MATLAB create the numbers in this matrix for a particular truss. But we need to understand how MATLAB is doing that, and for example, for the homeworks or for the quizzes, I can give you a very small truss with 2 or 3 elements and ask you to do the same by hand. So unless you know how to do it, the calculations would be not too complicated, not too cumbersome, but unless you know how to do it, it would be difficult. So let me then show you exactly this truss. And I'll use the MATLAB code. Hopefully you should have that in your handout. Let's see. So let's see. So on the MATLAB code that you have on your handout, I'm talking about this truss. Okay. So we have this input file. Hi. We are still in the middle of a class. Are you in this class? Could you wait outside, please? Thank you. So we have an input file for a truss. I hope that this input file makes sense to you. By the way, this input file is a text file. Unlike the MATLAB input files that you are using for your current version of the code, you can actually write a text file, just open up a notepad and describe the same nodes, elements, and there are 2 additional columns here. I'll talk about that in a bit. The other things are extremely similar to your current MATLAB version of the code, with boundary conditions, the supports at 1, 3, and 5, and the loads at nodes 2 and 4. That's all that this input file is describing, and hopefully you all can see that that's this truss. So in the MATLAB program, which is called Truss 2D Basic, which again I'll give to you, and once again, if you're still having trouble with the homework 7, the best way to learn MATLAB and how it's doing is to place a breakpoint at a particular line that you have questions about or have trouble, and then click run. So what happens if I do execute this line? Clear all, CLC, close all. Clear all swipes my memory of the MATLAB clean. CLC clears any commands that I have already here. And close all closes all figure windows. So let me execute that by pressing step F10. Okay, so that's that. I'm creating a tolerance just as before to find extremely small numbers for displacements or forces. So anything smaller than 10 to the minus 9, I'm going to treat it as 0. Here is where MATLAB is going to ask me for an input file. Unlike the MATLAB code that you have for homework 7, where we actually call a separate MATLAB.m file, here we are going to ask the user for the name of an input file, which is a text.txt file. So execute that, and yes, MATLAB asks me for the name of input file. So I'll pick the first example here, which is the truss there, and immediately I get the input file name from there. I'll execute this subroutine. This subroutine is get truss data 2D. So what it does is it goes into that text file and reads off all of the values um, of the input. So I have now in nodes, I have the node locations, x and y locations of all the nodes. In the elements, I have the connectivity, which element is connected to what. There is this matrix C, which is a matrix of Young's modulus. For each one of those, there are 7 elements, so there should be 7 cross 1. Indeed, it's a 7 cross 1 double vector of the Young's modulus for each of those elements. I have the area of cross section, I have boundary conditions, meaning support conditions, and the loads. So this is just reading the input file. The next 2 lines just calculate the number of elements and nodes. So execute both those. And number of elements is clearly 5. Number of elements is 7. Number of nodes is 5. And what I want to do next is create a big empty matrix of K, U, and F. So this K right now is a 10 cross 10 matrix of all zeros. That's the matrix that you started with on your homework, on this in-class assignment. Initially, it was all zeros, 10 cross 10 zeros. What we'll do is we'll ask MATLAB to fill in at the correct locations for each one of the elements in our truss. Okay. Similarly, the displacements, right now it's all zeros. The forces, it's all zeros, but we need to modify that. So the way we're going to modify it is by going through the boundary conditions. And what we'll do is I'll go up to this point, and what happens in this particular loop called boundary conditions, in this loop we determine which degrees of freedom are free and which degrees of freedom are specified. So clearly here, degrees of freedom 3, 4, 6, 7, 8. And if you look back at your notes, these are the same degrees of freedom that, for example, where was it? This guy. Yep, 3, 4, 6, 7, 8. We decided those were the degrees of freedom that were free degrees of freedom, the ones that we want to find. And the specified degrees of freedom were 1, 2, 5, 9, 10, which hopefully we can see here, 1, 2, 5, 9, 10. So that code, that piece of code, I'll let you figure out how it worked. But all it did was figure out among the 10 degrees of freedom, which ones are free, which ones are specified. Okay. And then we are adding the nodal loads, meaning the right hand side of this, here. We are going to add the known forces. We are going to add the known forces to the right hand side vector F. So this entire matrix that I asked you to construct by hand was the big 10 cross 10 zeros stiffness matrix. What we're going to do is add the loads 10 and minus 10 to the correct locations. So that's this part of the code. So I'll again place a next breakpoint here and click on go. Continue. So it goes up till there, and you can see F now is the correct force vector. There's no other known external forces on this truss. There's this force 10 kilonewton at node 2 in the x direction, and there is this minus 10 kilonewton at node 4 in the y direction. So you also should start looking at trying to relate or correlate the degree of freedom with the node number already. And here is where we are going to start constructing the global, that 10 cross 10, we are going to start filling in the values of those matrices. So as I said, it would be best done through a loop. This is the loop that we are going to use. So this loop says for I element going from 1 to the number of elements. I have 7 elements in here, so this loop will run 7 times, once for each element. So I'll take a step here, and currently IL is 1, meaning I'm dealing with element number 1, which happens to be element A in your handout. I'll take another step, and this L nodes is telling me that element 1 is connected to nodes 1 and 2. Okay, and indeed that truss, if you see, is connected to that. Node XYZ is basically the XY locations of node 1 and node 2. So one is at 0, 4, the other is at 3, 4. And then we get into this, this truss element 2D. This is the main subroutine or main function for the stiffness method. What it does is it takes the node locations of a particular truss element. You can tell that one node is here and another node is here, and you give it properties of that element, and it will give you out k element in the global coordinate system. Let's make sure that that's exactly what it's doing. And it looks like I won't go into this element routine today, but I'll show you how it's get assembled, and then next time I'll show you how the element subroutine gets constructed. So if I execute that, you should see that this K, this matrix, this 4 cross 4 matrix is KA11. Okay, it has something at 1, 1, 1, 3, 3, 1, and 3, 3, which is exactly the same as what we had for the local coordinate system, right? Something here, something here, something here, and something here. But I just said that this is the element stiffness matrix in global coordinates. So why is it that the global coordinate system matrix and the local coordinate system matrix for this particular element is the same? For element A, this is the last question. It's horizontal, right? The local coordinate system coincides with the global coordinate system. X prime, Y prime is the same as XY. So the transformation matrix doesn't do anything. It just takes the local coordinate, local stiffness matrix, and that gives you the same global matrix. All right, so let's stop here, and I'll show you how it gets assembled and gets created next time. And on your way out, please do turn in your in-class assignment, and I'll see you back on Monday. Yep, yep, one PDF.